Yes, sir. Can we start, sir?
Yeah, sure. So welcome to this live session 7 on principles of casting technology, uh, taught by Professor PKJ IIT Roorkee. So I'm one of the TA for this course. So I will be discussing these week 8 sessions. So this will cover some of the topics that is regarding filtering of casting, heat treatments for non-ferrous as well as ferrous alloys. Then we'll discuss casting defects, followed by the diagnostics in castings, are like some of the non-destructive techniques kind of. So before going to the this theoretical question, so this session is also a theoretical session. So you need to understand the process in order to attempt these questions. So I will be just briefly revising um, this whatever the topics taught by professor. So I will be using the same slides as professor used in the lecture. So it will be easy to you know discuss the things. So as you know, you might have already gone through this lecture. I will just briefly introduce to these things. Then we'll see these questions. So the first thing in this session is the felting of castings. It is also a shaking and cleaning methods. So this is like the post processing of casting, to be precise. So felting is nothing but it's an operation to cut unwanted material, then cleaning and finishing of the casting. So if you take any sand casting, preferably we need to do so much of post processing, starting with the breaking of the mold, then cleaning up the casting, then cutting unwanted portions such as this gate riser, the gating design we have to cut from the actual casting, then followed by the finishing method. So suppose if there are any ki- uh, kind of cracks or protrusions that are coming, unwanted protrusions, then we have to grind them off, or we need to cut them off. Okay. So after metal has solidified, casting is knocked out. So this is one of the thing that is mainly casting is knocked out by breaking the mold as early as possible. So after pouring the metal, so once we get to an understanding that everything is solidified, even if it is in red hot condition, we will just break the mold and we'll cool it in the surrounding air. So this is mainly for the sand casting. So this process, this felting is common word that is used for these castings, but it can be of different kinds. Suppose if you are using sand casting, this second point is applicable. But if you are using this say die casting process, that is not applicable. But if you use this for investment casting, this is applicable. So in such a way we have to understand. So this is the generalized way of post processing the casting products. Then the temperature at which the casting is knocked out of the mold depends upon the size and complexity shape of the casting. So this depends on the type of casting that you are going to using. Suppose if you have a thin sections and larger sections, so we have to ensure that everything is completely solidified, because the thin sections are easy to go to full screen, are easy to they will be easily solidified, whereas the larger casting they need some time to get solidified. So that is regarding this knocking off. So then once it is everything is done, we'll just break the mold and we'll keep this thing in the shaking station where it is manually. You can do manually or it can be a mechanical means in which this complete sand will be removed from this casting to the larger extent. But still we have to do the further steps in order to get the complete casting. So one is the knocking out of the dry and sand cores. So you might have know this cores, which are like uh, molds that are used to produce any cavities or internal cavities in the casting. So then followed by the, so these are the different steps in cast felting. Then followed by the removal of gates and risers. Then extraction of fins and unwanted projection at the different places. So these fins are these projections is will come. It's kind of defect you can say. So in which this metal when it is in higher very hot state, it will have very less viscosity. So it will easily go into the sand gaps, or if the sand grain is too large, so this metal will penetrate into it, and it will form some type of projections or some type of fins. So that we have to remove from this. Uh, okay. So you are still seeing the screen, right?
Yes, sir. Visible.
Okay. Just a second. Then the next step will be the cleaning and smoothing of the surface. Okay. So there is small problem with the laptop. I'll just rectify it.
Should I share the screen?
Uh,
Same
yeah,
slides.
yeah, that is also completely fine. You can share. So actually, my laptop has frozen, so I cannot edit that. Yeah, thanks a lot.
Sir, is it visible now?
Uh, Actually, I cannot see the slides.
Uh, just wait, sir.
Actually, my laptop has got just started.
Sir, is it now visible?
Yeah, yeah. You can go to. It's okay. My laptop just started. I can share. Okay.
Yes, sir. Yes.
Yeah.
Then I should stop, sir.
Okay. So I'm discussing these different stages in fettling. So I have discussed this how to knocking, then removal of gate sizes, then extraction of these fins and onward projection. Then comes the cleaning and smoothing of the surface. So we will be discussing in further slides what do you mean by the cleaning and smoothing as well. Then we follow up by repairing of the castings. So we basically we already uh, someone is unmute. Can you mute yourself? We are getting some. Yeah, thanks. Yeah. Then repairing of the castings. So what I was discussing is we have already spent enough time and enough material into it. So if there are small cracks, there is no need to discuss the product. Instead, we can do a little repairing itself. So, for example, if there is any small crack propagating, we can determine the crack size. If it is not detrimental, we can just weld it and grind off the surface. So that is one way to do this. Then if there are any blowholes, we can just impregnate with some type of resin in order to fill that hole. So this repairing we have to confirm of we have to proceed only if it is not much detriment to the structure of the casting product. Then straightening and are the wrapped or deformed casting. So this will happen if there is any wrapping of the warpage of the surface. So this is occurs mainly with the thin sections. So if you're knocking off the casting from the casting itself, so we have to ensure it is not there will be no warpage on the thin sections. Then only you have to knock from the sand mold, or else even though if there is any warpage, we can just straighten it off with using some type of tools. So these are the different types of fettling. So we will discuss one by one. We'll come to each and every point in detail. So first thing is the knocking of the dry cross. So this is simply the wrapping or knocking with an iron bar or pneumatic hydraulic device may be used in order to break this sand mold uh, so that we can take out the casting. So then we follow by the removal of the gates and risers. Depends in the size. So this removal depends on this size, shape, and casting of the metal. We can use hammer saws. We have to keep in mind if the casting is sensitive, then we should be careful while using this hammer saw. Then we can use flame cutting directly. So in order to remove this gating system, so where we generally we use oxyacetylene cutting, so that and we have to use, so we have three types of neutral frame, oxidizing frame, and carburizing frame. We have to use oxidizing frames so that it will completely cut the surface as well as remove it basically we use for cutting this oxidizing frame. Then sprue cutter for shearing of the sprues, or we can use abrasive cutting machine or plasma arc cutting. So this depends on the type of material we are going to cast and type of casting process we are going to use. So this is like the defects kind of removal of fins or unwanted projections. Either if the projections these generally these projections are not too large, we can just grind it off from the surface, or we can chip with just a hand tools. If it is very ductile brittle material, we can easily chip using this some type of tool. We can just chip off from the surface, or we can use some pneumatic tools just to remove that thing, or we can use this flame cutting as well. Then removing metals by arc or air equipment, then filling. So these are the different types of methods that we use to remove these fins or unwanted projections. This is also called as snagging, this removing of these unwanted projections or fins. So we should be careful that it does not affect the contour. So that is what mentioned in the end. So contour in the sense, if we have a shape for the casting while we doing this grinding or chipping, so it should not affect the dimensions of the casting. It should not reduce the dimensions. If it is reduces, then it is we have to discard it because we cannot add it. We cannot make into the actual shape. So we have to take care while doing removing these projections. Then come, so that is regarding the knocking of the casting. Then come the cleaning and smoothing. So we have this process called tumbling, in which we just put this white iron pieces, also called as stars. white iron pieces, you might have understood by the last class that these white iron are so hard materials, so that we cannot use actually in the practice. So we just make it malleable. We just heat treat it to produce malleable iron, in which we have a tempered carbon, so that it has some good toughness. So these white iron pieces will just pack with the casting. We'll just pack the casting and we'll just put in a big barrel which rotates. So while rotating, these white iron pieces and this casting will get collided with each other, and this unwanted, this cleaning and smoothing will be done on the casting product. And we have to make the casting tight, otherwise the casting we will keep so many casting at a time. So if we have to make it tight, so that this casting will not hit the other casting. If that happens, the casting will get damaged. So we have to keep the enough white iron pieces in between them. We can do this tumbling with hydroblast as well, with some kind of water jets, or we can use some air blast as well, which is called as sand blasting, in which we use this sand force very high pressure sand particles thrown onto the surface of the casting, which will completely clean the surface as well as remove the unwanted particles as well. Then come this shot blasting, so in which we use the small steel balls which will hit the surface. It will remove the unwanted portions, as well as it will induce some compressive stress on the surface of the casting, which is actually useful for the mechanical properties of the casting that is produced. Then we can use R care process or pickling process. So picking process is nothing but it is type of process that we use to remove the stains or unwanted oxide layers on the surface of any castings. So this pickling will just soak the casting part in some acid, say hydrofluoric acid, and then we'll remove it, and then we keep it in some neutralizing solution and we clean it off. So that is how the pickling works, in order to remove the stains on the surface or some oxide layers on the surface. So then comes to the major part, the repairing of the casting. As I discussed initially, if there is any small crack, there is no need to throw away the part. We can just weld it and grind it off. So that is what mentioned here. We can either use shouldering or bracing, or if there are any blowholes, we can just impregnate with the resin. Then comes to the epoxy. Even we can use the epoxy to fill those blowholes or any small defects. Then comes to the straightening. If there is any thin section which got warped during this casting knocking, so we can just use some tools to straighten it up. If there is any if the dimensions are undersized, we can just spray the metal paints in order to get the desired thickness. So that is what metal spraying means.
Sir, what is resin impregnation?
This is like if we have any small blowholes, some small pinholes, or any kind of effect, any kind of defects, we'll just put the casting and we'll put the resin and we'll apply some pressure, so that this resin will go into that blowholes and fill the gap. So that is what resin impregnation means. Okay.
Yes, sir.
So this is all regarding the fettling process. Also the like post processing of the castings. Then comes to the one interesting topic on heat treatment of castings. So this lecture is about this plain carbon and alloy steel castings. So we'll discuss the other non-ferrous castings in the next lecture, means next slides. So first of all, the need of heat treatment. So every casting product, which majorly most of the casting product need to be heat treated before it goes into the operations. So one of the main properties, modifying the properties, ensuring it has the properties that are reliable and repeatable. So that is what we have to focus. That is modifying properties. Then there comes the major thing, that is stress relieving. So while cooling from the casting, so there were so many residual stresses that could be developed inside the castings. So that may be due to several other factors, which are interesting thing, which is interesting though. So this is the stress relieving and modifying. These are the two important goals of this heat treatment. So basic what happens during heat treatment is nucleation growth of new nucleation growth of new precipitates kind of, or new grains, or so that is what happens. So we can basically the nucleation happens and then the growth happens. So this because in heat treatment we'll just heat it and reach some temperature and we soak it there. So when we soak it there, it whatever the nucleation happens, it grows. We'll see what are things that actually grows in this. So if you see this iron carbide diagram, uh, so basically heat treatment happens, if you see this line, this C, whatever C is happening. So basically we have austenite. So we based upon the type of cooling, we can actually predict the what is the microstructure in it. Suppose if we cool very faster, then we can end up with getting martensitic, very hard martensitic phase. If you cool it in such a way and soak it in such a way that we can get a fine perlite structure, or else we can get a ferrite structure, or we can get the binetic structure. So it depends on, so this line, this 9-10 degrees, whatever this A1, which is surrounding this gamma plus alpha, sorry, this all austenitic phases. So this is what we need to concentrate while doing this heat treatment. Okay, then let me explain the heat treatment of this plain carbon alloy steels. So basically, this figure itself explains everything. So this is the time temperature we call time temperature transformation curves, or TTT curves we call. So basically, this happens. This is for ejected composition of the steels. So if you see, this is the temperature 700 degrees Celsius, or we'll start with some 200 or 300 above that, where the austenitic is transferring into the actual phase. So this is where austenite. So we can start around some 800 to 900 degrees Celsius. Then if you cool directly, so this is the x-axis represent the time, that is the transformation time, and the y-axis represent the temperature. So, okay, suppose if there is any so now you have to define the slope of this. Suppose if there is slope is, if suppose if I say so if you see this at 750 at 100 degrees Celsius, we have mf. This mf, this is martensitic transformation finish. F means finish, M means martensitic. And at 300 we have M is martensitic and S is start. So this is the range in which we get martensitic phases. Suppose if you cool directly without touching this C curves, then we end up with getting martensitic structure. Suppose if you touch this the like cone, the first point of this curve, so you can see my cursor. So if you touch that and if you soak there itself, you will end up getting this perlaitic or upper binetic structures. So that is how it happens. Suppose if you cool these dotted lines, if you see the first dotted lines, and if you touch the this curve and if you soak it there, you will end up getting fine perlite. So everything is written here. Suppose if you end up, if you touch the graph here itself and if you soak it there, you will get a coarse perlite and fine perlite. So it makes sense, right? Because in the second dotted lines, your time is more, means you are holding it for a little more amount of time. So that is the reason you are getting coarse perlite, whereas in second you are getting fine perlite. So this is the perlitic region. Above that is the austenitic region. Here they have given the fine lamellar. This is the microstructure visibility of this type of microstructures with this type of phases. So this is the perlitic region. Then comes the binetic region. Then comes the martensitic region. Okay, now if you want in your phase, suppose in your steel, if you want binetic phases, so now then what you should do, you should touch this cone, then you should soak it there till it reaches the soak it there, then you cool it. So you have given these arrow temperatures down. So you have to wait till that time in order to get that type of structure. I hope this curves are like you got some idea about this type of curves. Then we have different types of heating in austenitic range and cooling. So one is the normalizing, full annealing, isothermal annealing, homogeneous annealing, hardening tempering, and Marr tempering and Nash tempering. So there were several other names as well. We sometimes we might have heard this process annealing as well. This full annealing or the process annealing. So let us discuss one by one. Then heating in Faraday range will be soft annealing, stress relieving, anti-flaking treatment. Okay. Okay, let me explain one by one. So in normalizing is like air cooling. So we'll just heat the what is whatever the component that we want to do heat treatment. Then once it is heated, soaked, everything is done, we'll just keep it in the air. So it is like a fast cooling when compared to annealing. So in full annealing, what we do, we just keep in the furnace and we just switch off the furnace. So we have very coarse type of grains in full annealing kind. So you can guess full annealing, the grain size in normalizing as well as full annealing. So in full annealing, we'll get bigger grain size, whereas in normalizing, we'll get smaller grain size when compared with the full annealing because it is cooling in the air. Okay. Then comes to the isothermal annealing. So so in this case, what happens is we suppose we are doing annealing at some 1000 degrees Celsius, say some 700 degrees Celsius. So we do annealing there, then we soak for some time, then we cool it to some 300 degrees Celsius, and we will hold there for some time more. In our so this depends upon the type of microstructures we want. Then after holding, we'll switch out the furnace. So this is like we are holding it for some at constant temperature for some amount of time. So that is what called as isothermal annealing. Okay, this is the difference between full annealing and isothermal annealing. In isothermal annealing, there is one more step adding to the full annealing, that is after cooling at some temperature, we'll again hold it. Then homogenization annealing. So this is mainly so all these annealing temperatures are done in that A3 curves that I have shown in the first figure. So this is the A3 or this is the AAC curve, this curve, which is the boundary of this austenitic and this alpha and gamma, and then right side we have gamma and cementite. So this boundary, so we whatever the composition you need, so we have to heat that till the temperature. Suppose if you need some around some 0.2, we have to go till around 768 degrees Celsius. Then we have to do the annealing process. So that is this is what dictates the highest temperature in that method. So that is full isothermal annealing. Then homogeneous annealing. So this is done. So what happens is during cooling. So this whatever solute is there, so it will segregate on the grain boundaries. So this homogeneous annealing is done so that this diffusion of these particles will happen into the. So we'll give some time for it to diffuse, so that instead of settling on the grain boundaries, it will actually go into the actual primary phase. So primary phase is the first phase that solidifies, so that this whatever the solute that is segregated on the grain boundaries, it will actually interact and it will redistribute in the entire region. So that is what we call homogenization. So this happens around 1200 degrees Celsius, whereas normalizing, annealing, this everything will happen around some 728, whatever the temperature range that I have given. So this, if you are using any alloying elements, so this happens only if you use some alloying elements or even the carbon. So this will carbon also will get some time to form some nice graphitic structure, or if there is any alloying elements that can get distributed in the region. So that is what happens in the homogenization annealing. So this in this homogenization, so there will be so many studies on this. So basically we call it as kinetic growths of this whatever segregation happening. So basically it will dissolve and it will form new phases, and it may form new phases, dissolve, it can distribute it evenly, and it can change its morphology. So many parameters happen in this type of homogenization. Then comes to the hardening. So you might have heard this hardening technique. So basically, we'll just you might have seen this experimental setup as well, end quench setup. So in which we just heat a iron bar completely red hot, and we'll put on the stage, and we'll just sprinkle water from the bottom from a nozzle, so that we can know how much depth it has gone hardening, means hardness is improved. So basically, this is done to improve the hardness of the component that we are using to certain depth, basically hardening. Then tempering. Uh, so this is done below some 400 to 500 degrees Celsius, and then kept for some time. So, same as the hardening, but hardening happens in kind of water, oil, or brain solution, whereas tempering happen in the normal atmosphere conditions. So hardening happens in water, oil, or brain solution. So basically, we'll get a martensitic transformation in the hardening, so that it has good wear resistance. Then we have martensitic and harsh tempering. So this I have explained it to you. So basically, in this TTT curves, we'll just go till the above the ms. So this is martensitic start temperature. So we'll go just above it, and then we just hold it there for some time, so that we'll get austenitic phases or kind of binetic phases in this. Suppose for martensitic, that is aus tempering, I think. Sorry, martensitic tempering. And aus tempering is what we do in this austenitic range. So this is austenitic range, just above and below. I think I'll throw some light on this too in following lectures always, in the next slide as well. Just hold for a minute. Then we have soft handling and stress relieving and anti-flating treatment. So so basically, this anti-flaking treatment is done in order to remove these hydrogen gases. Okay. Then this stress relieving, he happens at 500 to 600 degrees Celsius, and basically the name itself represents, it will just relieve the stresses or residual stresses that are developed in the this casting component. So soft handling. So these are the temperature dependent. Soft handling happens around 500 to 600 degrees Celsius, and we get this spherical shaped graphite in that, so that we'll get good toughness for the casting. So that is what happens in the soft handling and stress relieving and anti-flating treatment. So this treatment we do in order to remove this hydrogen gas actually, which is dissolved in the solid state component. Okay. So this is all about heat treatment in this steels, plain and alloy steels castings. Let me see the other. So any doubts in this? Okay. Okay. Let me explain this thing as well. Then I will go to this question, numerical questions. So this is retreatment of cast irons. Still now we have discussed only for steels. Now we'll discuss for cast irons and non-ferrous metals. Okay. Uh, so heat treatment for cast iron. So basically, this cast iron you might have known very hard compared to the steels, because we have very good amount of carbon present in this. So basically, we do this heat treatment just to improve its machinability, wear resistance. So you might have. So I will explain how you can improve wear resistance using heat treatment. Then you can improve strength, and you can improve dimensional stability and stress removal. So this is all the three different goals that we do. Goals for the heat treatment of this gray cast iron. So first thing is improve it machinability of gray cast iron. Generally, these cast irons are easy to machine because we have this graphite present in it, so it kind of act as a solid lubricant. So we just do subcritical annealing. So basically, subcritical annealing is the temperature is around 600 to 700 degrees Celsius. So in that subcritical annealing, uh, we do this heat treatment so that we get spheroidization of perlite and some degree of gravitization. So this perlite, and we get the, in order to get this periodization of the perlite and some degree of graphitization. So you might have known this graphitization is nothing but forming this graphite in the microstructure of this cast iron, so that it has good because it graphite is comparatively soft. It helps in so many aspects. One is this improves the strength, good damping capability, and good machining. So complete dailing results into complete gravitization and soft iron. Then permanent mold castings are fully annealed. So basically, permanent mold castings, such as this die castings, I can say, are fully annealed because uh, they are subjected to very high cooling rates. So that is the main reason we just anneal these. Normalizing at high temperature retains perlite and gives high strength and hardness as compared to the form of annealing. So normalizing at high temperature retains perlite. So that is I showed in that CCC curves. The first range is itself the perlite that forms at high temperatures, which has very good properties in terms of hardness and strength as well. So then comes the wear resistance. So this is main application of this heat treatment. So generally we have so many gears that are used in our automobile or any type of equipment that need very good wear resistance. We just heat it to very good high temperature, then we'll just quench it in oil or water. So in that it may completely transfer into martensitic structure, or only some thickness will, like core will transform into martensitic structure, which is having very good wear resistance, whereas inner will be ductile, like ferrite or perlitic structure, so that we'll have both very good hardness on the surface as well as very good toughness of the component. So that is what this wear resistance improvement by using heat treatment. So this can be any type. We can do quenching as well as tempering. So basically, there will be followed by two heat treatment process. We can do quenching as well as tempering at various temperatures. For example, here they're giving example of cylinder liners. Firstly, they quench the iron, then they also follow this tempering process. Then comes the flame or induction hardening may also be carried out. So we'll discuss this flame or induction in detail. So this is the basic idea. So we have to improve the strength, hardening, followed by tempering it, produce optimal tensile properties. The first thing is stress relief. So these are the conditions that we need to follow. So basically, we have to heat the whatever the casting component to a specified range. Not we have to keep in mind we are not touching above the solidus line, uh, below the solidus line, but optimum temperature range will just heat it. So and we should not change the this microstructure to not to a great extent. Even after annealing, we'll go first this so after this quenching, we'll go for the stress relief, so that we'll get some, even along with the hardness, we'll get some toughness in the component. So that is what happens in stress relief. So basically, when you quench any object or when you solidify any object very quickly, so this residual stresses will not be relieved on the object. So that is the main reason that we go for this annealing or normalizing operations. So this is the time has given they again for hour or more, cooling slowly from 200. These are the temperature range for this cast irons. So now comes the manual cast iron. As I have explained earlier, this is done for white cast iron. So basically, white cast iron is very hard substance, and we get these carbides in it. So which is not easily usable in actual scenario. So we just heat treat it in order to get manual iron. So in the last class we have discussed. So we'll do this heat treatment for about from some 40 hours, and we have that cooling curve as well, that heat treatment curve as well. So basically, it has three steps. First, basically, our main goal is in white cast iron we have so much of carbides. We just hard carbides, so we just have to break them, and we have to nucleate this graphite formation, or which is known as graphitization, that we need to promote. So that is the main step. So the first step will be nucleation of graphites. So this will be the end of the, so from room temp, suppose if we are going from room temperature to some 870 degrees Celsius. So when we reach this 870 degrees Celsius, then this nucleation starts, this graphite nucleation start. So this occurs during heating to high holding temperature and very early during the holding period. Okay, before holding, it starts, nucleation starts. Then we have first stage graphitization, that is known as FSG. So where we'll hold at 870 to 970 degrees Celsius. So this graphitization will promote, this nucleation promotes, and it will, graphitization happens. Then we start slow cooling through allotropic transformation of iron. So we get the second stage of graphitization. So this is graphitization happening in two stages, first stage and second stage. The first initial step one is nucleation, then first stage graphitization, and second stage graphitization. In first stage, we'll just hold it. It happens during holding. The second stage graphitization happens when we start cooling. So we heat it, we hold for this for some time, then we cool it gradually. So this is the malleable iron. This is the heat treatment process in malleable cast iron. So we have perletic malleable iron as well. If you want to get perletic structure, so we have to add this magnesium, this about 0.5 to 0.9% in order to retain this perlite in the structure. Uh, so that is, this is one of the nucleating agent in order to retain the perlite, as well as in the cooling curves as well. So initial phase is the perlite, so we have to hold for a long time, so that cooling should be more in order to promote the hold of this perlite. Okay. Then complete SSG. This is second stage graphitization is prevented by adding alloying elements such as magnesium, molybdenum, chromium, so that it will remain in the perlitic stage itself. It will not convert into graphite. It will stage in perlite by just adding this magnesium, molybdenum, or cerium. So that is what we are arresting during second stage of graphitization. Okay, in this malleable iron, in the second stage also we have graphitization, but here we are adding some alloying elements, or we are using these alloying elements, and we are arresting this SSG, so that we are getting this pelletic, we are retaining the pelletic structure in the malleable iron microstructure. So now come to the ductile iron. So in ductile iron, anyway, the name itself implies it is ductile, but still we have to go for this annealing, uh, and so that we will get even more ductility and machinability. So this matrix consists of ferrite and spherical graphite. So the graphite is present in the shape of spheres, small spheres, if you can visualize, which are distributed on the entire microstructure. So basically, we have to reduce this magnesium, phosphorus, chromium, etc. should be as low as possible, so they retard the process. Okay, so this graphitization, so these might reduce the formation of this ferrite and graphitization, so that we have to keep them as low as possible. These are like property oriented heat treatments. So normalizing of ductile iron, nothing but air cooling, results into homogeneous structure of fine pellet and improved in tensile properties. Okay, these are like have important role. Normalizing is commonly followed by the tempering. So these are we already discussed what happens during normalization. Here they have given you some type of alloying elements in the heat treatment as well. We'll see. Yeah. So this is what I reserved for the discussion. That is hardening and tempering of ductile irons. So basically, it gives very high hardness. So hardening and temperature, as I discussed, we just dip it in oil or water or brain solution as well. After quenching, castings are usually tempered. Okay, tempered is nothing but we heat it to some 200 to 300 degrees Celsius and we cool it gradually. So basically, surface hardening, this happens by flame or induction process. So basically, we can take an induction heater and we just if you keep on the surface, it will just heat this only the surface to very red hot condition, or we can directly use flame as well. So here we use oxyacetylene flame with any kind of post forward or backhand type of kind of flames. So basically, perlite type of ductile iron are preferred because short heating cycles of this process. Iron without free ferrite respond initially to flame induction heating and require no holding time at austin temperature for getting fully hardened. So see this, irons without free ferrite responds initially to flame induction hardening. Okay, so the and requires holding time at a hosting temperature for getting fully hardened. So one thing to remain is this surface hardening is that so this flame is contains some kind of carbon as well. So when you heating on the surface, this carbon will actually diffuse into the surface and it forms this cementic structure, which is hard structure. So that we'll get hard surface on the hard layer on the surface itself. So that is one surface hardening technique that we use by the flame as well. So that is what here iron without free ferrite responds instantly flame induction heating and require no holding time at all. At austin temperatures for getting fully hardened. Fully hardened. Then stress relieving for this cast iron, sorry, ductile cast iron. Then austempered ductile iron. So austempering that happens in the first stage of the TTT curves, which having very good toughness with high strength. Structure consists of two phase mixtures, that is alkyl binetic ferrite and austenite. So if you but austenite is still unstable phase as well. So austempery reaction, it happens in two phases. Austenite decomposes into binetic ferrite and carbon enriched austenite. In the second, unprolonging, that is nothing but soaking in the temperature range, the austenite temperature reaction, carbon enriched austenite decomposes into ferrite and carbide. So this is how what happens during the austempering or austempering ductile iron. This is like the first stage of the TTT. The second stage is the perlitic. The next stage is the binetic, and the last stage is the martensitic transformation. So now comes to the heat treatment of non-ferrous metals or alloys. The first thing is homogenization. So it is not. It is to remove the coring or dendritic segregation. So coring is suppose if you coring is a like non-uniform composition. So if you assume a circle, at the center we'll have some higher composition of one element, and at the periphery we'll have the composition of some other element. Say suppose if you take copper and nickel, at the center we have nickel 100%. Then when we gradually coming from the center to the periphery, this nickel percentage is reducing and copper is increasing, and that is how this composition vary, and that we call as coring. So that we can remove by this heat treatment. Then dendritic segregation, as I earlier explained. So while this primary phase, suppose in this case, suppose if copper is forming, copper is primary phase, if I assume the copper is forming, then it will reject the nickel whatever in the phase. So if you remember, if you assume one grain, when it is that which is a copper grain, so if which has some dissolved nickel in it, it will just reject into the grain boundaries. So that is known as the segregation, that is finally end up on the grain boundaries, which can be diffused using this homogenization technique. Then we have this alloy. So that is what happened. This is the process. Alloy is heated to elevated temperature for several hours, during which homogenization of composition occurs through the action of diffusion. So this choice of suitable homogeneous temperature is limited by the Sodus line as well as the retardation of the process. So this is also I have explained. So we have to select the temperature such that it should not go above the solidus. It should be below solidus, and it will actually initiate this homogenization process because if you go above solidus line, it will just melt away. So that is the basic line we have here. Basic rule we have in this heat treatment of this non-ferrous alloys. So this is also one of the important technique, that is the age treatment. Suppose if you take so we have some elements, suppose aluminum, copper, aluminum, magnesium, aluminum, magnesium. So these are the different types we have. So basically this solubility is very less in this. But if you suppose if you mix aluminum and copper, and if you cool it very suddenly, so it will not have any time to diffuse, so it will solidify. But when you heat treat it, what happens is this copper or solid whatever, it will form precipitate, then it will come out from the actual mixture and it will form precipitates, and these precipitates actually impede the dislocation moment and improve the mechanical properties. So that is what this age treatment known as. This can happen naturally, or you can actually do alloy heated into temperature where homogeneous single phase form, followed by quenching and further aging temperature ranges. So this is how we do the aging treatment. We'll just heat it, then we'll quench it, and we can further aging the temperature and quench it. Okay, still we get the good precipitations. When we do this heat treatment, we'll get the precipitations. So that is what this age treatment mainly applied for the aluminum alloys as well as magnesium and copper also. So that is about this heat treatment in non-ferrous alloys, in these cast irons as well as non-ferrous alloys. So meanwhile, we'll do some numericals. Sorry, some theoretical questions before going to the next part of the discussion. Yeah. Just read the question, and I think we can read this later when I explain these defects. Yeah. Please read the question. And
Both are correct. Option C.
okay. Any other answers? Okay. So the heat treatment of steels is concerned with the transformation of austenite to perlite. Okay. In ejected steels, carbon composition is 0.08%. We have to see this second option, then it is fine. Just let me check the composition. So generally 0.08 is for plain carbon steels.
Yes, it is a point 0.8 for it exact.
Okay,
So I think it is wrong. Option 2 is wrong. So
correct,
it,
correct.
A option can be the.
So this is for I guess plain carbon steels. If you can see. Okay, so this is correct. So we have only option A.
But sir, in heat treatment we also get like benite and martensite. So how we can say austenite to perlite only?
Uh, so basically, we concentrate on perlite because of its properties. Yeah, that is true. Like it is, I can say correct in this scenario. So you are correct. So basically, this austenite too, we can get binite as well as martensite as well. But we also getting this perlite, right? So basically, we do this heat treatment in order to get this type of structures only, perlitic structure. Very rarely we use for binitic or martensitic.
Okay, sir.
So let us go to the next question.
Sir, not clear.
Okay. Yeah, I will explain.
Sir, what is dendritic segregation?
Okay, I will explain that also. Okay. So, which of the following statements is are correct? In the case of homogenization, the heat treatment of non-ferrous alloys, okay, homogenization of the composition occurs spontaneously through the action of diffusion. Okay, that is true, but I am little concerned about the spontaneously. But this statement is true. Then dendritic segregation associated with the inhomogeneity in composition occurs because of the thermal and constitutional supercooling. So basically, this dendritic segregation is suppose if we have say this is the domain and we have this solidification happening. So basically, in this type of structures, we'll get this type of dendrites. Okay, so now solidification is happening in this way, and gradually these things will increase in size, and finally they solidify. So basically, what is happening in this time is so this is the primary phase. We generally denote with the alpha, and it will reject the solute into the solution, solute rejection into this region wherever there is no this is in still liquid state. So this is the solid that we have, and this is all liquid. Okay, so here in the center also we have liquid, and it will reject into the outer side. So what happens at an instant, this solid will not have any like way to escape into into the actual liquid and solidify. So it will get trapped here itself, and when you see the actual microstructure, we'll have grains like this, and at this region we'll see that this solute segregation happening. So this is known as the dendritic segregation, as segregation, solute segregation in large view. Okay, understood. So
Sir, what
this
is
happens because
constitutional
yeah.
supercooling? Sir,
Okay,
because of
yeah,
thermal
yeah.
and constitutional supercooling. Thermal means
Conscious
heating.
supercooling. Yes, thermal is nothing but we are just cooling it. We have this graph, right? So this is temperature and this is concentration. So what is happening when we cool from higher temperature to lower temperature? Gradually, we are from liquid we are getting solid. So that is what thermal supercooling. Supercooling is nothing but like it is kind of cooling, but even it is cooled, it is still in liquid phase. It is not solid. So that is what supercooling means. Then comes to the constitutional. Constitution is nothing but the composition. Okay. Now see in this graph. So when you are coming till this point, say this is liquidus, say this is solidus. So in this phase we have both this liquid plus solid. Okay. So what is happening is this. So this actual melting point is this. This is the melting point. Say uh, T1. I'm proposing T1 here. So what happens is that it will reject the since it will reject the this concentration, whatever the solute rejection that I have explained in this figure. It will reject the heat, this concentration, this solute into the liquid. So what happens at this? If you see this composition is increasing when you this rejection is happening, this composition is increasing. So at that time, what happens is we have T2 means other composition in which it has lower means. So this is what the composition we actually have. say aluminum 10% copper. But what is happening due to this rejection, the actual melting point is decreased. Now in this phase, T1 is great, like T2 is less than T1. Okay, so it can it has lower melting point. So what happens? It will solidify. Means if you come in the reverse order from the liquid to solid, it will solidify faster. So that is what constitutional supercooling. So in that case, if you see here, I have shown progressive solidification. The dendrite is growing in this phase, but in actual, when dendrite is growing in this phase, because of this constitutional supercooling, which is the supercooling happening because of the concentration difference. So we'll get some one more dendrite formation here, and it will also grow. Some more, one more dendritic nucleation, then it will also grow starting because of this constitutional supercooling. Because of that, also we'll get this dendritic segregation again, or kind of solute segregation. So finally, what your takeaway will be? So this segregation is associated with one is this thermal supercooling. The second one is this constitutional supercooling. I should not tell thermal supercooling. I should just tell thermal gradient. So these are the two factors for which this segregation to happen. Okay.
Yes, sir.
Okay. Okay. Let me quickly explain the
So,
other
sir,
parts as well.
these both
Yeah.
statements are correct. Option C.
Oh, sorry. Both the statements are correct. Okay. Because this is also correct. This is also correct. But it may not happen spontaneously. It takes some time. So this can be like partially correct, kind of. Because if it is happening spontaneously, there is no
Yes, sir. It
like
needs time.
sense.
Yes, sir.
Yeah, it actually needs time. Okay, let me quickly explain the other parts as well, then we can answer the other questions. Okay. Okay, Arsi, so we have completed this. Let me go to the diffection casting. I think you already know some of the casting defects that we already discussed
Yes, sir.
previously. Yeah. So one thing, let me briefly discuss. So this slide will completely like list out all the type of defects. So this can be classified based on this. What is the reason behind that defect? The first one is gas defect, which is blowholes, open blows, or air inclusions, or pinhole porosity. Okay. Then the shrinkage cavities, which are occurring due to the shrinkages. Then molding material defects, cuts, washes, metal penetration, fusion, runout, rat tails, and buckles, swell drop. Then pouring metal defects, mist and cold side slag inclusions, and metallurgical defects such as hot tears or hot spots. So let me come from the first one, gas defects. So this happens due to the dissolved gases in the liquid state. So basically, this solubility will decrease when it transfer to solid. So that is the reason these gases will escape, will try to escape from the mold itself. If we have very good ventilation provided, this permeability of this sand is good, then this gas can easily escape. But if the permeability is not so good or not exactly correctly designed, so this gas end up in the casting itself, which forms these blowholes, like then open blows. This can be seen on the surface. Then air inclusions, so type of air inside the casting. Then pinhole porosity. This pinhole porosity is especially for the hydrogen. So this hydrogen, when dissolved, it will just from the inside the casting, when it starts solidifying, so it will just try to escape from the top of the casting. So while it will travel from the both center part to the top center, or wherever it is, it will travel to the top and it will leave its path actually. So which looks like a pinhole. That is the pinhole porosity occurring due to the hydrogen. Then we have shrinkage cavities. So basically this is also same. uh, the density, this is occurs due to the density difference between the liquid and solid. So the density of the solid is more when compared to the liquid, so that there will be a decrease in volume in order to accommodate it. Okay. So the liquid, so that in the solid state the size will decrease, the volume will decrease when compared to the liquid. So that is what the shrinkage cavities occurs. If we did not provide enough enough material, enough liquid, then this shrinkage cavities occurs. So there these shrinkage cavities can be in millimeter size as well as in micron size as well. So these shrinkages can happen in grain size level as well. So this gas and shrinkages we like differentiate just by the shape. So in gas defect is, they are more likely perfectly spherical or elliptical, but shrinkage are very irregularly shaped. Then come to the molding material defects, which has metal cuts, washes. So these are nothing but the projections from the castings. Then metal penetration. So this is also kind of metal we get penetrated into this bigger grain sizes. Then fusion. This is nothing but if the this refractability of the sand is not so good, it will get fused on the surface of the casting. Then runout. This got not completely filling the, I think that is misrun. We'll discuss what is runout. Then rat tails. This is also projection, but the shape look like a rat tail. And buckles swell and drop. Okay, if you see these figures, the first one is a microporosity, the small dots that you can see. Then mold. So this is contact the blowhole or the sand blow. This, and this is blow which is open to the, which is on the surface. And these are the pinholes that I discussed, the small pinholes that are actually will be within, in one region we can see so many types of holes. So this is shrinkage cavity that happens on the center line. It can happen inside as well. Then we have cold shut, where if you are filling this type of castings, if you see the liquid will come first here, then it will fill the bottom part. When this is completely filled, then it will travel from left as well as left as well as right directions. So it will have two different thermal gradients, so they will not fuse well. So so which forms this cold shut effect. So then we have this metal penetrations on the surface, and we have misrun. This occurs because if this solidifies, premature solidification happens, this casting will not completely fill. So this is the one type of defect. Then we have this metallurgical defects, this misrun, cold shut, and slag inclusions. This slag inclusions happens if you are not providing enough, if you're not clean. One thing is, if you see in this type of castings, so these slags are of two kinds. So one will be the means high density slags and low density slags. So these slags will form, these are the unwanted oxide layers, whatever that forms during this pouring into the metal. So you have to provide them as skim bobs. So one thing, you can keep a like uh, some sprue well, we can say this sprue is there, then we can provide some base so that the heavier objects will be collected there. And we similarly, you can provide one well on here also, so that lighter objects will be collected on the top. So that is the one way in order to remove this type of slag inclusions. Then we have metallurgical defects such as hot tears and hot spots. So basically these are occurs if you did not have any like unyielding supports. This occurs as well as if there is no directional solidification happening. So in that case, if one part will solidify earlier than the other, if you have a lighter region or thinner section there, like bigger section, it will be still in the liquid state, and there you can see these hot tears or hot spots. Okay. And yeah, if you have any doubt in this, you can just look on the, like we have provided only few graphs here, but similarly you can get graphs for hot TS as well. So if you assume a high section, for example, so the both the flanges will both the flange will solidify later. First the other web section will try to solidify, and they try to kind of shrink. So due to that shrinkage, if there is any spot where still it is in liquid state, there we can get a shearing kind of action, and there we can see this hot tear formation. So that is one good example for hot tears as well.
Sir, what is the difference between hot spots and shrinkage cavities?
Hot spots and shrinkage cavities. Okay. Hmm. Okay. Hotspot. How to explain hotspot? Hotspot is the last region which solidifies. You got it? Suppose if you take a cube which is completely inside the sand, if you are filling it, which will be the last spots to solidify? The center of the cube, right?
Yes,
That
sir.
will be in still liquid when everything is solidified. So what happens from the center? All the uh, kind of all the liquid will be absorbed by the surrounding layer. Then we get this hot spot. But whereas shrinkage can happen anywhere, right? They are kind of related. Shrinkage. So here you can see shrinkage happening. But hotspot, as I explained, it will be inside the shrinkage. Can be also inside. You can say these are kind of related, both of more or less effects. But hotspots you can actually predict because it's the last certifying region. Okay. And one more thing. So here they have mentioned shrinkage cavity here itself, but mainly in general castings, shrinkage cavities and gas cavities are of same order. If you see, suppose gas cavity are more or less in micron sized, so shrinkage also are of same order. Whereas hotspots, I think there are some two orders higher than shrinkage cavities, kind of.
Okay, sir.
Like you can understand hotspots as last solidifying regions, that is called as hotspots, whereas shrinkage are like cavities that formed due to the shrinkage effect. Then I will finish with this final topic, that is the diagnostics in castings. Nothing but non-destructive test techniques. So we have, these are the different types of techniques. So these are in actual standards, in casting or folding. These are the standards that need to be passed for any casting in order to keep this in service. So NDT is a very famous technique, non-destructive technique. So basically, mostly we use this radiography, costly, but radiography. Then ultrasonic is like well used everywhere. So let me discuss one by one. So visual inspection, then magnetic, then dye penetration test, then radiography, fluoroscopy. There are more or less related fluoroscopy and radiography. Then ultrasonic, then we have eddy current technique, then we have pressure testing. Let me start with the magnetic particle testing. So basically, if you see in the right side figure, we have a surface. On the surface, we have a crack. Basically, we disperse this magnetic powder or whatever solution on the top of this, and we'll just apply the magnetic field. If there is any crack, we can clearly see this. Okay, I cannot show. So wherever there is a crack, we can see the disturbance in the magnetic field. So that gives an indication for us, like there are the cracks in the surface. So this is magnetic particle testing. Then we have dye penetration test. This is also very famous an NDT technique. So basically, suppose if you have a this mainly applied to bearings, you can say easily bearing bushes that if you are going to cast. Suppose it is very simple technique to be followed. If you have a crack, first clean it with some solvents. Apply that this dye. Basically, these are colored dye. Then we have to clean the surface and we have to wait for some time to sit. Then we have to add this developer so that it will swell. That dye will swell and will try to come out, so that you can see where exactly the crack is present in the surface. So if you see liquid containing a colored dye or a substance that emits a green or yellow light when involved in a, so this is also okay, but in general we can see actually that whatever the crack happening, we can see through our visual through our naked eyes as well. Even you can use this light sensitive materials as well. Then we have this radiography testings or fluoroscopy. So basically, this radiography works on the principle of density difference, or like how a material reacts with a type of X-rays. So basically, the contrast. Suppose if you have, for example, if you're in the right side figure, we have a cracks. So these are not easily passing through, so that we can easily get some contrast difference between the parent material and the crack, so that we can easily guess guess the defect present on the casting. So penetrating ionized radiation are passed to the component. Selection of ionizing radiation is dependent upon the absorption coefficient of the material. So this in fluoroscopy images are produced on the fluorescent screen. So in fluoroscopy images are produced on the fluorescent screen, which will be directly you can see in situ. This test you can see in situ as well. So basically, we have one more technique in this radiography. This is radiography. We also have X-ray, like tomography also, in which we can get a 3D scan. In this also we can get 3D scan with some setup. But in tomography also we can using the same principle, X-rays, and then we just keep some setup stage such that it will rotate in 360 degrees, so that we can get the complete 3D structure of an element, which is popularly used nowadays. Then we have this famous technique, ultrasonic testing. So basically we'll have a transducer which will produce these ultrasonic frequency ranges. Suppose suppose if there is no crack, it will take some time to get into the. We'll have two things: transmitter and receiver. If there is no crack, so there will be one time difference. If there is a crack, there will be some more time difference for this sound wave to travel. So that we can see on the monitor, and based upon the time difference, we can get what is the length, what is the depth of the crack, every detail we can get from the these things. Then we have eddy current techniques. So basically, it is This is how it works. If they, so basically here they have shown you only one. So we have a this coil, and will if you apply some potential to it, it will induce some eddy currents on the surface of the object, and these eddy currents will again generate some magnetic field, which will be detected by the secondary coil. So this is the primary coil we are showing. There will be one more secondary coil as well. So we'll just see the phase difference between these two, the primary and secondary coils. And if there is any crack present, we'll get some difference in that. We'll do first, this is a two-step process. First you have to do on a surface where there is no crack, then note the readings, phase difference, everything, then do on a crack. So if there is any crack, these eddy currents are disturbed. So based on that we can get that phase difference whatever, and we can measure the crack. Then we have leak detection. I think this is a leak detection testing. One is the bubble test and helium mass spectroscopy test. So this is nothing but we'll just keep the component in water, and we'll just apply some very high pressure. So what happens? This water will actually go into the whatever pinholes that are present. So generally, due to the surface tension, this water will not go. But if you apply enough pressure, this water will go, so that you can see the bubbles that are coming from the object. So that is how you actually see the defect present in the component. Similarly, we can use this helium mass spectroscope as well. Both are more or less works on the same principle as well. So these are some of the NDT techniques that we use for inspecting these castings. Okay, so let us solve some questions quickly. Yeah, you can read the question.
Sir, option B, swell. A swell is a
B.
yes, sir.
Okay.
Sir, not swell. It is shift, sir.
Okay.
Sir, it is swell only, swell. Because shift is due to misalignment of cope and drag. Cope shift,
Yes, yes.
cope shift. Right.
Okay. So a dash is an enlargement of mold cavity by metal pressure caused by insufficient mold pressure. So let us come to the first option, shift. So this is also called as drag. Okay, that is the improper alignment of cope and drag. Then we have swell. Let us discuss later. So blowholes is also we have a casting and we have these holes inside. Then porosity. This is also more or less same, but this can be of different types. One is gas as well as shrinkage. So only the option is remaining is swell. So basically, this is the enlargement of the cavity, which is occurred by the metal pressure caused by insufficient mold pressure. Okay, so how it looks? Suppose suppose we have casting and we have good amount of we just filled with the liquid. So if the supports are not enough, so we get this swell, right? We, we actually we need this type of product, but due to this enlargement, we get extra this type of defect. Okay, Ex- because of this occurring only because of this insufficient mold pressure on the this liquid whatever is coming. So we have to, so this we can take care of this by selecting proper good strength sand as well as good ramming on the sand. Yeah.
Sir, just scroll down, please. Actually, the question is not visible.
Fine.
Yes, yes, sir. Sir, you can zoom, sir, little bit.
Zoom. Okay.
Sir, option A, I think, but because it is not Misran, not cold set, and not hot.
Okay. Okay, dash is caused by the expansion of the surface layer of the sand. Oh, this is also something related to scab. Okay, only. So Misran is, I think I have shown in some one figure. Suppose if you have this type of casting, we just we see it is like incomplete filling of the casting. That is Misran. Then cold shut is like we have these two types. Best example for cold shot will be this hollow portion, because in this type only we have two types of streams. One thing will go from here this direction, one will come from this direction, and will they join and they form this cold shot because there are incomplete. This is occurs due to incomplete fusion. Incomplete fusion of two metal flows. Okay. Then we have hot air. Hot air, simply we can go with this I section. Suppose we have this type of casting, then we are easy can get this type of defect. This occur with, so the remaining is scab. Scab is nothing but this expansion only. Okay, let us read.
Sir, erosion scab.
Yeah, correct.
Option B, sir.
Yeah, option B is the correct one. So expansion scab is already we covered. Cold shot also we covered. So this is the erosion scab. If the metal velocity is little much higher or it is in turbulent stage, there is a chance of erosion of the sand, and there we can get this scab as well. Okay, so I will explain this. Yeah, this is the scam. Let us explain. Go to the next question. Any idea what is this hot tear?
Sir, option C, hindered contractions.
Yes, option C is the correct one. So basically, this is how hot air, high fluidity does not lead to hot tearing. High melt temperature, no low coefficient of thermal expansion, no, should be high. So this is the correct option, hindered contraction. So similarly, suppose if you have this type of thing, suppose the mold, this is the mold, this is the mold surface. Okay, if this mold surface is not yielding, means so what happens? It is kind of a rigid. So if in this case, so we have a So suppose this is solid. So this is completely solid. This is also completely solid, and it is coming at the center. Means I'm just giving a scenario. So now what happens? Here we have still some which are in a little bit of liquid state. So what happens? This complete body try to contract in this direction, and this try to contract in this direction, so that we have a weak portions here. I'm just giving an example. This might happen. So we have a weak sections here and here, where there is a chance of tearing of the casting. So that is what happen. What is called as a hot tearing that occurs due to unyielding. One reason is this rigid supports of the molds, or else the hindered contraction. So this contraction is hindered by this type of molds. Okay, so this is called as hot tearing defect.
Option A, sir.
Okay, the slide is visible, right?
Yes, it is visible, sir. Clearly
Yeah.
visible.
Okay. So misstone in casting areas due to poor fluidity of the molten metal, poor green stain, low porosity, and high superheat. So this is a direct question. So this occurs due to the poor fluidity. So how to avoid this? One is select high pouring temperature, and
Sir, your screen is not visible.
yeah, I'm checking.
Shubham Jaiswal is presenting.
Okay. Why?
Stop presenting.
Actually, I have no that. I'll just check. Can you stop your presentation, Shubham?
Sir, you can stop him at your end.
Yeah. Actually, I did not find that. Okay.
No, no, sir. See in the view and right click and just send them out. Then it is possible.
Yeah, I think it is coming up. You can see, right?
Yes.
So I am discussing about this misrun in casting. So one is you can select high pouring temperature. At the same time, you should be aware of this gas porosity. If you are going at high temperature, there is chance of this gas solubility increase in the molten metal. So the other thing is low freezing range alloys. This also you can get. Then the other is gating design. So this you can take care of in order to reduce this mistron. Okay. Yes. Okay. Continue.
Sir, it is called Shatna. You have told us right now that when two streams are not fusing with each other, it is called.
Yes. Yes.
It is clear,
Okay.
sir. It is clear, sir.
Okay. So I think everything is covered. So cold shut is the correct answer in this. You should see this imperfect fusion of two streams. Okay, let me see the other one. This is regarding this testing inspection of casting.
Yes, sir. Both are correct. Option C.
Okay, so let me read. A dye penetration test is used to detect the surface from the casting, which is correct. Ultrasonic inspection is used to test the internal defects of the castings. Both are the correct. Both are correct options. Okay. Let me know if you have any doubts. I'm just because we already discussed, so I'm just scrolling up.
Yes, sir. Both are correct, sir. D.
Okay. Okay. Let me read. So the transducer is used to convert electrical energy into sound energy. Okay, that is true, and it can be the other way also. Then magnetic particle inspection test can not be used for non-magnetic materials. Yeah, that is also true. If it is not magnetic material, then there is no like magnetic field going into it. So both options are correct. I think that these are the questions. If you have any doubts, I will explain this run
Yes.
out.
Next slide, sir.
This is the last question. We already discussed the other questions. Okay.
Right.
So I will explain this run out. So this is nothing but so we have a casting, but there is a leakage occurred in that casting. So due to that, the casting is not completely filled. So instead of this is the casting we want, but it is not completely filled.
Short pouring.
Due to leakage of this molten metal. Okay, that is this runout defect. I think the other defects are almost similar. And yeah, this is all about it. And one more thing I missed is so in this, okay, assume these are the TTT curves. I will end the session with these two topics. So here we have this T equilibrium temperature or static temperature. Then we have this perlite region, this binetic region. I think. Then we have this martensitic region. Okay, so martensitic, this is the region where we are getting this austenitic tempering, and this is the region where we are getting this martensitic temperature. So this is like, suppose if you want to do martensitic temperature, we should not touch this point. We should come like this. Then we have to hold here. So this is the heat treatment process. So this you will get this martensitic structure, the, like our needle like structure. In this arch tempering, so we will come, and here we will hold, so that we get this binetic structure as well, plus Austin as well. So we'll get both this binetic structure as well as austenitic structure. So this is to the basic difference between this austenitic tempering as well as this martensitic tempering. Yeah, this is the last session, which will explain the weeks. So there is one more session coming up. So in which I will mostly focus on these numericals, just the revision on the numericals for the exam. So
Yes.
next session will be kind of revision session.
Okay, sir. Yes,
Okay.
sir. How many numericals we will get in this casting?
I have no idea actually. So this paper was prepared by someone else.
Right, sir.
Okay.
Okay, okay. Fine.
But just go through these assignments. That should cover everything.
Right, sir.
Okay. So if you have any doubt, just ask me. Otherwise, you can leave the meeting. Thanks for joining.
Thank you, sir.
Thank you, sir.